Up until now, we have been specifying what a system may do. The main purpose of this lecture is to explain how to specify what a system must do. It's based on a single example, the alternating bit protocol, a simple algorithm for sending data across a channel that can lose messages. In part 1, we specify what the protocol should do. We will specify how it does it in part 2. But before we get to the protocol, we learn about the TLA plus operators for using a very important data structure, finite sequences, which programmers often call lists. Finite sequence is just another name for tuple. So this tuple is a sequence of length 3. Remember that this tuple is typed like this, where the angle brackets are typed double less than and double greater than. A sequence of length n is a function whose domain is the set of integers from 1 through n. This sequence of length 3 applied to the number 1 equals its first element, the sequence applied to the number 2 equals its second element, and applied to the number 3 equals its third element. The sequence of the squares of the first n positive integers is the function which, when applied to the number I, equals I squared for all I in its domain, the integers from 1 through n. That function is usually written this way, where the exponentiation operator is represented by the caret character. The standard sequences module defines some useful operators on finite sequences. The tail of a non-empty sequence equals the sequence obtained by chopping off its first element. And since it would be funny to have a tail without a head, we call the first element its head. The concatenation operator, which we type \lowercase o, concatenates two sequences, as in this example. Any non-empty sequence is the concatenation of the one-element sequence containing only its head with its tail. The append operator appends an element to the end of a sequence. The operator len applied to a sequence equals the sequence's length. Note that the domain of a sequence is the set of integers from 1 to the sequence's length. Note also that 1, 0 is the empty set, which is the domain of the empty sequence. The seq operator applied to a set equals the set of all finite sequences formed from the elements of that set. For example, seq applied to the set containing the single element 3 equals this infinite set of sequences. For later use, let's now define the remove operator. So remove of I_seq is the sequence obtained by removing the ith element of the sequence seq. The length of remove of I_seq should be 1 less than the length of seq. So remove of I_seq should be defined like this to be a function whose domain is the set of integers from 1 to the length of seq minus 1. We just have to fill in the ... A little thought shows that the definition should be this. Well, a little thought when you're more used to writing specs. It might be a lot of thought now. So we should check this definition. Here's how. Create a new spec with this body, which you can copy from the web page. Now create a new model. The model's model overview page will show that there are no behaviors to be checked. TLC can still check assumptions. On the model checking results page, enter an expression to check, such as this one. Run TLC on the model. TLC will compute the value of the expression. In this case, checking that remove has the right value for these arguments. You can evaluate a constant expression on any model, with or without a behavioral spec. The Cartesian product. For any sets S and T, their Cartesian product S cross T equals the set of all pairs AB with A in S and B in T. That set can also be written like this. The cross operator is typed \X. Stop the video and let TLC compute this 6-element set. Now see what happens if you remove the parentheses. You get an error because this is how that expression is parsed. The cross product of 3 sets is the obvious set of triples, and so on for the cross product of any number of sets. In the alternating bit protocol, we abbreviate alternating bit as AB. In the AB protocol, a sender A sends a sequence of data items to a receiver B. Let's suppose for now that those data items are strings. Here's an obvious way to represent this. The states of A and B are represented by 2 variables, AVAR and BVAR. They're initially set to some default value, say the empty string. If A wants to send a string, say the string Fred, it sets AVAR to that value. B must eventually receive that string by setting BVAR equal to it. A chooses a new value, say Mary, which it sends, and B receives, and so on. What sequence of values was sent? Obviously the sequence Fred, Mary, Ted, and Ann. No, it was actually this sequence. Didn't you see AVAR change from Mary to Mary and BVAR do the same thing? And didn't you see them changing from Ted to Ted twice? Of course not. A value can't have been sent if nothing changed. How can we let the same value be sent twice in a row? By adding something to the state that can change when the value is sent for the second time. We could add a variable clock and let the value in AVAR be sent again when the value of clock changes. But we'll take a different approach. We'll let the values of AVAR and BVAR be ordered pairs, the first element of which is the value being sent, and the second element is a 1-bit value that is changed when a value is chosen. So we can send this sequence of values like this. The spec of what the AB protocol is supposed to accomplish is in a module named AB spec. As usual, it extends the integers module, and it declares the constant data, which is the set of all values that can be transmitted. We declare the spec's 2 variables and the type correctness invariant, asserting that both variables are pairs whose first element is in the set data and whose second element is either 0 or 1. It's convenient to define vars to be the tuple of all variables. The initial state formula asserts that AVAR can equal any pair whose first element is in data and whose second element is 1, and BVAR must equal AVAR. We're going to define A to be the action in which the sender A chooses a new value to send, and we're going to define B to be the action in which the receiver B receives a value. The next state action permits an A step or a B step. And here's the complete spec. Remember that vars was defined to be the tuple of all variables. Now for the definition of action A. The action can be taken when AVAR equals BVAR. The new value of AVAR is a pair that can have any data value as its first component and whose second component is the complement of AVAR's original second component. A programmer might write that complement this way. A mathematician might write it this way, where percent is the modulus operator used in many programming languages. TLC will show you how it's defined for negative arguments. We'll write it like this, the way a bright child might. The action leaves BVAR unchanged. We now define action B, in which a message is received. A B step can be taken when the values of AVAR and BVAR are unequal. The step sets the value of B var to that of A var, and it leaves A var unchanged. This completes the definition of the specification spec. Stop the video now to download AB spec and open it in the toolbox. Create a model that substitutes a small set of model values, perhaps containing 3 values, for data, and run TLC on the model to check that type OK is an invariant. Type correctness doesn't mean that a specification is correct. To find errors, we should check that formulas which should be invariants actually are invariants. Here's one such formula defined in the AB spec module. Convince yourself that it should be an invariant and have TLC check that it actually is. Like all the specifications we've written so far, formula spec asserts only what may happen. We will now specify what must happen. But first, we look at exactly what may and must mean. A safety formula is a temporal formula that asserts only what may happen. More precisely, it's a temporal formula that, if a behavior violates it, meaning that if the formula is false on the behavior, then that violation occurs at some particular point in the behavior, and nothing in the behavior past that point can prevent the violation. For example, the kind of specification we've been writing can be violated by a behavior only if either the initial formula is false on the behavior's first state, or the action next sub vars is false on some step. Remember that this action false on a step means that the step neither satisfies the action next nor leaves the tuple vars of variables unchanged. And nothing in the behavior past that point of violation can cause the formula to be true. A liveness formula is a temporal formula that asserts only what must happen. More precisely, it's a temporal formula for which a behavior cannot violate it at any particular point. At any point in the behavior, there's a way to complete the behavior so it satisfies the formula. An example of a liveness formula is one asserting that x equals 5 on some state of the behavior. We'll see in a minute how to write a formula that asserts this. At any point in a behavior, it's always possible for x to equal 5 in some later state, so the behavior isn't violated at that point. Remember that a behavior is any infinite sequence of states. We're not talking only about behaviors that satisfy some specification. X equals 5 is true on some state of the behavior is asserted by this temporal formula, where this symbol is typed less than, greater than, and pronounced eventually. The only liveness property sequential programs must satisfy is termination. It's expressed by the formula eventually terminated for a state formula terminated which asserts that the program has reached a terminated state. Concurrent systems can have a wide variety of liveness requirements. Here's a liveness property we might like the AB protocol to ensure. If A var equals the pair high 0 in some state, which means it's a state in which A is sending that pair to B, then B var equals this pair, either in that state or in a later state, which means it's a state in which B has received the pair. That property is expressed in TLA+ by this temporal formula, where this symbol is read leads to and is typed in ASCII as tilde greater than. In general, we'd like the AB protocol to satisfy this property. Any value being sent by A is eventually received by B. This is expressed as follows. For all V in this set, which is the set of all possible values of A var and B var, A var equals B leads to B var equals V. As an exercise, convince yourself that eventually P is equivalent to not always not P. Enabled. Let A be an arbitrary action. A is said to be enabled in a state S if and only if there is some next state T such that A is true on the step from S to T. Instead of saying A is true on the step S to T, we often say that S to T is an A step. As an example, remember action A of AB spec, which is defined like this. For it to be enabled, the first conjunct must be true. A conjunct with no primes is an assertion about the first state, so it's an enabling condition for an action. We can obviously choose values of A var and B var in the next state to make these two conjuncts true, except that the second conjunct is false if data is the empty set, so data must be non-empty for A to be enabled. Weak fairness of action A asserts of a behavior that if A ever remains continuously enabled, then an A step must eventually occur. For example, suppose we have a behavior and A enabled is false in this state, then true, then false again, then true, and it remains continuously true. Then an A step must occur in this green part of the behavior, after which A need not remain enabled. An equivalent way of saying this is that A cannot remain enabled forever without another A step occurring. Weak fairness of A is written as this temporal formula, where vars is the tuple of all the specs variables. It's typed as WF underscore vars parentheses A in ASCII. It's usually read WF of A, omitting the vars. I'll explain the vars later. WF of A is a liveness property because at any point in a behavior, it can be made true by an A step or a state in which A is not enabled. Later, in the second part of this lecture, we'll see the strong fairness formula SF of A. A TLA plus spec with liveness is written in this form, where fairness is a conjunction of one or more WF and/or SF of A formulas, and each A is a subaction of next, which means that every possible A step is a next step. Module AB defines fair spec to be this specification, where WF of next asserts that a behavior keeps taking next steps as long as next is enabled, which means as long as the system is not in a deadlocked or terminated state. And the safety part of the spec implies that such a state cannot be reached. So the behavior must keep taking next steps, with A sending and B receiving values forever. Clone the model you've created for AB spec. For liveness checking, your model must not have any symmetry set. If it does, change it. Set its behavior spec to fair spec. Have TLC check that fair spec satisfies this liveness property, which we looked at before. You can copy it from the web page. Here's another possible high-level spec of the AB protocol, which has this fairness requirement. Action B is enabled when the sender has sent a value that hasn't been received, and it remains enabled until a B step occurs. This spec requires every sent value to be received, but allows the sender to stop sending at any time. Here's an exercise for you. Explain why these two formulas are equivalent when init, next, and so on are defined as they are in module AB spec, and use TLC to check that they really are equivalent. Here's what that vars subscript is all about. Remember our definition of weak fairness of an action A. WF of A actually means weak fairness of the action A and vars prime not equal to vars. A step of that action is a non-stuttering A step. We add the non-stuttering requirement because it makes no sense to require a stuttering step to occur, since there's no way of telling whether it did. You now know what the AB protocol is supposed to do, but you still don't know how it does it. And what is this mysterious strong fairness? Tune in to the second exciting part of this lecture to find out. Meanwhile, you'll be happy to learn that sequences are the last of the commonly used TLA plus data types that you need to know. And you've seen almost all of the built-in TLA plus operators on those data types.